Greetings, AP Chemistry students. This is Mr. Harper, and we're here live in Gullah, California. And today what we're going to talk about is significant figures. There's a lot of questions I've been having about significant figures and how they work, and so in this podcast we want to try to briefly explain them and their significance and use in chemistry. Okay? Basically what significant figures are is when we're talking about numbers, significant figures is a way of describing, keeping track of how well we really know a number. Okay, this is important for accuracy when we're doing calculations and measurements in the lab. Okay, so for example, let's take a look at this picture over here, which is depicting a graduated cylinder that's partially filled with a liquid. Okay, now you should all remember from last year that when you read a graduated cylinder, you read the volume from the bottom of the meniscus. And so, of course, if you're looking at this graduated cylinder, I asked you, well, what does it read? You say, well, of course, Mr. Harper, this looks like 30, 1, 2, 3, 4, 5 milliliters or so is the volume of the liquid in that graduated cylinder. Okay, well, these two digits right here, okay, 30 and the 30, and the 5 here, these are numbers that we know exactly. They're certain, okay, because there's marks in the graduated cylinder, for 30 and then for each 1 milliliter after that, okay? So whenever we're making a measurement in chemistry lab, so whether it's with a graduated cylinder or a ruler or a balance or what have you, we're always going to add in, we're going to estimate the next place, okay, the first uncertain number. In this case, to me it looks like this is exactly on 35, so I'm going to report this number as being 35.0 milliliters right here, okay? Now, what this tells me, this is important. Even if, it's exactly on the 35, there's no real fraction there, that 0 tells me this number is measured to the 10th place, and this is accurate to the 10th place, okay? If I look at this number, you're going to understand this later on in the podcast, but this number would have 3 significant figures, okay? Now, this is the correct way to report this volume, or, if you thought it was a little bit above 35, you might say 35.1, or a little bit below 35, you might say 34.9, but it should be somewhere there in the neighborhood. This last digit is a little bit up for debate, but nothing else really is, okay? Now, say we're going to record this number differently. Say I wrote it down as being 35 milliliters. That is a bad measurement, and the reason why, guys, is because we can measure this volume more accurately than 35 milliliters. We can see it falls exactly here on that line, so we can say it's at 35.0 milliliters. This number is not accurate as written, is not accurate enough, okay? This has only got, as you're going to see, 2 significant figures, okay? And it's not an accurate number, so we're not going to, we wouldn't write it down like that. In a similar fashion, guys, we also would not write down the volume like this, as being 35.00 milliliters. You might ask me, well, Mr. Harper, why not? If we have 1 0 here, well, then 2 is obviously better. Well, that's true, but this is actually too accurate. If we look here at the thing here, we can estimate to the 10th place. This place is estimated, but we have no information at all about the 1000th place or where that rests at all. This number we have no capability to estimate. As we see later on in the podcast, guys, this number has got 4 significant figures. It is too accurate. We cannot measure with that accuracy, and so, of course, we would not do that either, okay? So, significant figures are a way to keep track of how accurately we really know something, okay? And we're going to go over here in this podcast the rules for using them in calculations. So here we go. If you're watching this podcast, you should take notes. Okay, here we go. And by the way, I totally lifted these rules. There's similar statements of these in different textbooks, but I totally lifted these rules from a guy named Mr. Reed. He's another chemistry teacher, and so we're going to use these here in our class as well. Non-zero digits are significant, okay? This is called the non-zero rule. What do I mean by that, okay? If we look here at this number, 2.45 centimeters, a length, okay? All these digits are non-zero, therefore, they're all significant in this number. So this number has got 3 sig figs. Okay, there we go. Pretty simple, okay? So 1, 2, 3 numbers means 3 significant figures. All right. Rule number 2, which is called the straddle rule, okay? Zeros between significant figures are significant. So, for example, if I was to measure a different length and report it as being 2.03 centimeters, this 2 and the 3 are significant. The 0 in between, then, therefore, is also significant. So this number has got 3 significant figures, digits that I know exactly. Okay. Rule number 3. Zeros at the end of the number and after a decimal point are also significant. We're going to refer to this as the righty-righty rule. So, for example, If I look at this number, 7.850, we have a 0 here. Now, zeros are not always significant, okay? But here, this 0 is at the end of this number, and it is after a decimal point. This is an important point, guys. It's at the end of the number, and it's after a decimal point. Therefore, if I see this number written down, I'm going to say this has got 4 significant figures in it, okay? Rule number 4. For whole numbers ending in 0, the zeros are not significant. For example, if I look at this number as written, 71 million, okay, we have a 7 and a 1. Those numbers are significant, but these numbers, the zeros that come after, if the number is written like this, is not significant. This turkey here would have 2 sig figs, as it is written, okay? Now, does that mean we can't have a number that is exactly 71 million? No, it doesn't mean we can't have that, but let me show you some exceptions here to that rule, okay? Say, for example, we have that number 71 million, okay? That number, as it is written, like we just showed, has got 2 significant figures. But say that I actually had a number, say I was in a bank and I had 71 million $1 bills, and I knew that number exactly, and I wanted to write that in such a way that it would be understood that it is exact, okay? Here's the ways we can do it. Number 1, okay? Use scientific notation, okay? 71 million, as I have it written here, okay, I could also write as being 7.1 times 10 to the 7th power. These numbers both, as written, would have 2 sig figs, okay? But say I wanted to write 71 million to be exact, okay, and to have, all those numbers be significant. Here's how I would do it. I would say 7.1000000. These 6 zeros here following that 1, and then times 10 to the 7th power. If I was that bank teller with 71 million $1 bills back there that I was counting, okay, this would be a way to record that data, okay, in such a way that all these digits were seen as being significant. This number would then, therefore, have 8 significant figures, okay? The other way, okay, way number 2, to denote that all the zeros count, okay, when you're writing down a number, is use a decimal point, okay? Okay? Say, for example, we're still using the same number, 71 million. I could say that all those zeros are significant by just slapping a decimal point right here, guys, at the end of the number. That says that all these... Oops, sorry, guys, got to pause. We get a phone call. Guys, we are back. So like I was saying, the second way we can denote that all these numbers are accurate is by using a decimal point. If we place the decimal point here at the end of the number, that says that all these digits are accurate and they effectively count. So again, this is the same thing as doing that, okay? So this would also have 8 significant figures if it was written that way. In the same way, guys, say I had something like a number 10, I don't know what it is, say 10 grams. That number right there would only have, as written, 1 significant figure, okay? If you were writing that down as, some data or on a piece of paper or something like that, and you wanted to show me that it really is 2 significant figures, that both these things count, you can do it like this. Either say 1.0 times 10 to the 1st power in scientific notation grams, or you say 10 decimal point grams. I like scientific notation better, but suit yourself in matters such as this. Okay. Here we go, guys. Continuing on with the rules. Rule number 5. When the measurement is less than a whole number and the 0 is to the left of the decimal, the 0 is not significant. Okay? So this is talking about decimals. Alright? For example, like this. 0.02 centimeters. Here we have a number. We have zeros to the left of that number. When you have zeros to the left, those zeros are not significant. This number only has 1 significant figure. Okay? In the same way, this turkey right here, okay, this is actually kind of a composite of several rules. We have 2 1s here. These are followed by a 0. This number, as we previously said, to the right of these numbers is significant. These guys here to the left of the decimal, those turkeys are not. So this has got 3 significant figures, okay, in that number. Last rule, guys. Number 6. If a number is counted or known to be exact. It is considered to have an infinite number of significant figures for the purposes of calculations. For example, say we get back to school on August 17th, guys. It is coming up on August 17th. Say we come back to school on August 17th, and we get all in the classroom, and I count that there are 35 students in that classroom. That number is counted. It is exact. So for the purposes of calculation, anything I might do with it mathematically, it has an infinite number of significant figures and will not limit the accuracy of my final number. Okay? So things that you count, infinite number of significant figures. Also, where this is really important, guys, is with conversions. Okay? Conversion factors. Say, for example, I use this equality. 1 meter is equal to 100 centimeters, and I use these conversions, okay? This conversion factor right here is considered exact. It's 1 meter is defined as 100 centimeters, so we wouldn't be limited by the number, by, whatever. These each have an infinite number of significant figures for the purposes of a calculation. We're going to do some examples later on, and that's going to make more sense when we do that. Okay. Some rules now. How do we use this in calculations? Okay? Here's an example. For multiplication and division, when we do multiplication and division, we round our answer to the least number of significant figures. These rules we're going to go over, guys, affect how we round our answers, okay? For example, say we're finding the area of some object, okay, and we have two measured lengths, 6.221 centimeters and 5.2 centimeters, okay? 6.221 centimeters. This turkey has got 4 significant figures. This one here has got 5.2 centimeters, has got 2 significant figures. Now you can see here, guys, that this number is measured to the thousandth place. We know that pretty well. This one is only measured to the 10th place. This one is less accurate than this one is, okay? So let's go through here and do our calculation on a calculator. I've got my trusty TI-84 Plus graphing calculator, which I would recommend if you're looking for a calculator. 6.221 times 5.2 is 32.3492 centimeters squared. Okay, always put the unit on there, guys, because a naked number in chemistry is meaningless. Okay, now, this number here, okay, now, if we look at this, if I write this down when I got off my calculator, that wouldn't make any sense to report my answer that way, because now this answer is to the 10,000th of a square centimeter, whereas I didn't even know that here before. So we need to round this number. We're going to round this. Okay, if we look, how do we round it? We're going to look at our two numbers here that we had as inputs. We're going to use the least number of significant figures. This one here has only got 2, which means my answer, when I multiply or divide, is only going to have 2 significant figures. If I round this to 2 significant figures, I get 32 centimeters squared. And there we go. That's the answer to that question right there. Okay? Now here's an interesting point, guys. As I'm going to exhort you later on, you're only going to do this rounding stuff at the end of a problem, okay? So if you're doing this like halfway through a problem, we're going through and doing some multiplication or division, you never want to round at the end. But say you want to show me in your work that you understand you've only got 2 significant figures here. Here's how to do it. Here's a convention we're going to use in AP Chemistry, and also it's going to be understood on the AP test. If I want to show this number only has 2 sig figs, but I want to carry out these decimals here for the purpose of a calculation or whatever, I'm going to underline the figures that are not significant, okay? If you do that on a quiz or a test or your homework, I will see that and know that you know this number right here has only got 2 sig figs. And there we go. Okay, that's multiplication and division. Next, let's look at addition and subtraction, okay? That's a little bit different. When we round after doing addition and subtraction, you're going to report your answer to the fewest number of decimal places, not necessarily significant figures. Let's see how that works, okay? Say now we're working with masses, and we're taking 20.4 grams, which has 3 sig figs, and we're subtracting 1.322 grams, which incidentally has 4 sig figs, okay? Now notice, this has got 1 decimal place. We only know that to the tenths. This has got 3 decimal places. We know that to the 1,000th of a gram. That's pretty good, okay? So if we do this subtraction on our calculator, 20.4 minus 1.322, okay, we're going to get 19.078 grams. Okay? Now, when we round this to get our final answer, we're going to round to the least number of decimal places, which is, if we look here at our input numbers, what we start with, okay, the least number of decimals is in this number. This has only got one decimal place. Okay, guys, sorry, we got to pause again. So when we round this number, 19.078 grams, we're going to round it to the tenths place, and so when we do that, it's going to be, the answer is 19.1 grams. And there we go. So that's how we round when we're doing addition or subtraction. All right. A couple notes I'd like to make here. Number one is that when we're doing calculations in chemistry, you can gain or lose significant figures during the course of a calculation. For example, say we're working with mass here. We have two things rounded together, say 5.0 grams and 6.0 grams. Say we're adding those turkeys together, and we get the answer here would be 11.0 grams. Following our rule here for rounding with addition, we're still going to round to the first decimal place. There we go. Okay. Notice this number here that we're taking has 2 sig figs. This has got 2 sig figs. This turkey here's got 3 sig figs. Okay. So in this calculation, we've actually gained a significant figure. That can happen. And the converse is also true. Say we had 11.0 grams, we subtracted from it 5 grams. The answer would be 6.0 grams. But if we do that, this has got 3 sig figs, this has got 2, and so the answer here is going to have 2. In this case, we lost a significant figure. That can happen during the course of calculation, and it is okay. Okay? And the second point I wanted to make here, a second note, that's something you should write down, is, I said this before, but I'm going to say it again because it's very important. Always round to the correct number of significant figures at the end of a calculation. If you do it in intermediate steps of the calculation, you're going to introduce rounding errors. That decreases the accuracy of your answer, and it is bad. Okay, so always, always, always do this at the end of a calculation. If you want to just do your other stuff on your calculator and then round the answer at the end, that's totally fine. Okay. Okay, let's look at an example of how this would be applied in an actual problem. Okay, so we're going to go to chapter 2 and problem number 46. Okay, let me get my pen back here. It seems it has left. Okay, so here's what it says. Superman comes from the planet Krypton. If you have 0.00789 grams of the gaseous element krypton, which has a symbol of Kr, by the way, how many moles does this represent? How many atoms does this represent? Okay, so this is actually kind of like 2 parts. I'm going to say that moles is going to be part A, and this is going to be part B. Okay, so let's look at how we would set this up. All right, this looks like to me like the given right here. So we're going to start our dimensional analysis problem with the given, which is 0.00789 grams. Okay. Now I'm going to convert that turkey into moles. To do that, I'm going to use my handy periodic table that I gave you guys before we went on summer vacation. If I do that, we're going to use here the molar mass. It says that krypton has a molar mass of 83.80 grams per mole. I'm going to use that conversion factor upside down because I want to get moles on top. 1 mole is 83.80 grams. I'm going to go through here and do my multiplication and division. Okay, grams cancels, I get moles in my answer. Okay, if I do the multiplication and division on my calculator, 0.00789 times 1 divided by 83.80. Okay, I'm going to get this answer right here. 9.41527446 times 10 to the minus 5th power. Okay, but it wouldn't make any sense to report my answer like that because I don't actually know this accurately. Okay, here we're going to go to significant figures to determine how we're going to round, okay? This number here has got 3 sig figs. This number here has got 4 sig figs. When we multiply or divide, our accuracy is limited by our number that has the fewest number of significant figures. In this case, that's going to be 3, okay? So we're going to round this turkey here to 3 sig figs. If I do that, this is going to turn into 9.42 times 10 to the minus 5th power, and our unit here is going to be moles. And there we go. Okay. Hope you see how we did that. Now, part B. We want to convert this turkey into atoms. Now, you might be tempted to say, well, I know the number of moles, guys, or I know the number of moles, Mr. Harper, and I know that every mole contains 6.02 times 10 to the 23rd power atoms of krypton, and so I'll just change that into that. And that would actually be the wrong approach in this case, because that would be rounding in an intermediate part of the problem. So we're going to start again from the beginning. 0.00789 grams. Okay, we're going to change that into moles. 1 mole of krypton is 83.80 grams. And now here, grams goes away. I'm going to change my moles into atoms. Okay, 1 mole, which will cancel now, contains 6.02 times 10 to the 23rd power atoms of krypton. Okay, now there we go. Now again, if we're going to round our answer, guys, okay, we see this number that we're starting with has 3 significant figures. This turkey has got 4, and this one right here, we're going to say is infinite, actually. The mole to particle conversion we'll say has infinite sig figs for the purposes of calculation. Okay, if we go through now and do that, on the calculator, 0.00789 divided by 83.80, okay, and then multiplied by 6.02 times 10 to the 23rd power, we're going to get our answer is 5.67 times 10 to the 19th power atoms. And there we go. So hopefully, guys, that made the whole idea of significant figures clear to you. I hope you're having a good vacation, and I will see you when we get back to school, which is on August 17th. Till then, enjoy the rest of your summer. Hasta la vista.